Hey guys, hope you're doing okay. We're going to talk a little bit about acids and bases, which is something that you guys have probably come into contact with, maybe sometimes without even realizing it. But acids, you definitely have eaten some acids before. You might have drank some acids. You've used them on your skin. There's lots of different things with acids that you guys have done. So just a couple things about acids is that they do taste sour. So a lot of times that you eat a really sour candy, they have an acid on the outside of it to make it taste super sour. Okay, acids produce a hydrogen, which is a proton, which increases the concentration of hydronium. So we've talked about before that hydrogen can't exist in water by itself. It's really attracted to that polar water molecule, so that hydrogen jumps on and it produces hydronium. So acids essentially produce hydronium. And that's one way that you can tell if it is an acid is based on the hydronium content of the water. Okay, because it does produce those ions, they are good conductors of electricity. And another property is that acids react with metals and they produce hydrogen gas. Remember that hydrogen is that diatomic. So if you ever have to write an equation where you're writing hydrogen gas, don't forget that you do need that H2. Don't just put H. So make sure that you do H2 in order to make sure that you account for that because it's a diatomic. Okay, a couple examples of acids. And again, I know that you've heard of some of these. We will also talk about naming acids at another time. So right now, HCl is hydrochloric acid. That's found in your stomach. Nitric acid is HNO3. H2SO4 is sulfuric acid. That's found in car batteries, for example. Citric acid, so your citrus fruits. Acetic acid is also known as vinegar. So there's definitely been lots of acids that you guys have come into contact with, and you may or may not have known at the time that you had an acid. Okay, bases. Bases are obviously different from acids. A couple of their properties: bases have a bitter taste. They feel slippery. So, for example, if you've ever had your mouth maybe washed out with soap for whatever reason that you can tell or not tell me later, but if you've ever had your mouth washed out with soap, you know that it is a slippery feel. It tastes really gross, but that is a property of base. Bases produce hydroxide ions. So hydroxide is OH. So bases also will conduct electricity because it produces those ions. Okay, so here's an example. NaOH, I know that it is a base because it has that hydroxide ion in there. And notice that as a solid, now if I put it into water, it dissociates or it breaks up. So that Na ion is now separate from that hydroxide ion. So this is specific to bases. Okay. And then alkali metals, that very first column on your periodic table, and alkaline earth metals, when they're formed with hydroxide, form really strong bases. So KOH is potassium hydroxide, lithium hydroxide. Okay, those are some of your sodium hydroxide. Those are your alkaline metals. And then your larger alkaline earths, so calcium hydroxide, magnesium hydroxide, those are strong bases. So a lot of the bases are soluble in water and they completely dissociate. Now, magnesium hydroxide is technically not soluble in water, but it will completely break apart when it's reacted with an acid. So it is considered a very strong base. Think about bases. A lot of times they're really concentrated, like Drano or lye. Lots of cleaners have bases in them, phosphates, carbonates, things like that. So there is a very simple definition of acids and bases brought to you by Arrhenius. Now, Arrhenius was really the first guy to come around and really kind of talk about acids and bases and what those actually mean. So according to Arrhenius, acids produce hydrogen ions in aqueous solutions, so that hydrogen, the proton there, and then bases have hydroxide ions in their formulas, and then they dissociate and it breaks up in their aqueous solutions. Arrhenius definitely gave us the most basic. A lot of acids and bases do have this stuff. So acids and bases are easily identified this way, but it's definitely the most simplified version of it, and it didn't cover everything. And we'll talk about that again in a little bit. So if I was going to describe acids, here acids produce that hydrogen. So again, that's hydronium because it can't exist by itself in water. So here, for example, you can see this acid in water, okay, produces that hydronium ion. So that hydrogen here, it dissociates and then it jumps right onto that water molecule. So again, it breaks up, and because H and H2O don't exist separately, that's where you get the H3O from. And then because this H left this element, now you have that element by itself. Okay, or again, strong acids. Strong acids completely dissociate, completely breaks up into ions. Hydrochloric acid, for example, is a very strong acid. So you'll notice that it is going to completely break up into its hydrogen and chloride ions. So when you are looking at this list, you need to know your 6 strong acids. So make sure that you definitely write these down. So HCl is hydrochloric acid, H2SO4 is sulfuric acid, HNO3 is nitric acid, HBr is hydrobromic acid, HI is hydroiodic acid, and then HClO4 is perchloric acid. And again, those are strong acids because it completely breaks up into ions. It donates that hydrogen out front. Notice all of them have a hydrogen at the beginning of that compound. Well, it donates that hydrogen to the water, or to, if it's reacting with a base, it can react with water or a base. And when it's mixed, it'll completely give off its hydrogen. Okay, so that's the strong acids, and you definitely need to make sure that you know what those are. Okay, we can measure the strength of an acid by what's called the pH scale. So pH stands for potential hydrogen, and you can calculate it, and we'll talk about calculating it at another time. But the pH is the negative log of your hydronium ion, or your hydrogen content there. So it is a log scale because the hydrogen concentration, your hydronium concentration, is so small. Usually it's like times 10 to the negative something. And because it's so small, if you make it into a log scale, we can have the numbers 0 to 14. So making it into a log scale just kind of eases how we describe acids and bases with its pH. So the pH scale does go from 0 to 14. If it has a pH of less than 7, it is considered an acid. It could be a 0.5, a 2, a 6.9, whatever it is. But if it's less than 7, it's an acid. If it has a pH of 7, it is completely neutral. And then if it has a pH greater than 7, all the way up to 14, that is going to be considered a base. All right, I'm going to switch over to, So initially, we talked about Arrhenius was the first guy to really describe what an acid and a base was. So Arrhenius said, acids have an H, and the hydroxide is with the base. So that didn't cover everything completely. And because it didn't cover everything completely, it was kind of expounded on later by Bronsted Lowry. So Bronsted and Lowry kind of came along later and said, you know what, there's more to acids and bases. That definition doesn't really describe everything. So they came along and they described acids and bases a little bit differently. So they kind of added on to it. So an acid, according to Bronsted and Lowry, are proton donors. And again, proton, that hydrogen, it's the only hydrogen, or the only atom. It's got one proton, one electron. It's the only atom with no neutrons. So that hydrogen atom has no neutron, one electron, one proton. Well, in order to become a positive charge, it has no electron. It's just that one proton. So when you see the term proton, as far as acids and bases go, it's talking about that hydrogen. So it's a proton donor, or you could just say it's a hydrogen donor. Either are totally fine. So what that means is an acid is going to give up. It's going to give away that hydrogen. And according to Bronsted Lowry, a base is a proton acceptor. So a base is going to be one that accepts it. So it's going to take it in. Okay, so they kind of used their definition to fill in the gaps of what maybe didn't totally make sense with Arrhenius. So Bronsted Lowry definition would include ammonia. So ammonia, you need to know this, is a really common weak base. And if you look at it, it doesn't have that OH like Arrhenius first described bases as. So the Bronsted and Lowry definition includes NH3. So it doesn't have that OH in its actual formula, but if you notice in the equation, it actually produces OH, and that's what's going to make it a base. So if you look here, I have my ammonia, NH3. I'm going to react that with water. And again, I've mentioned this before previously. Think of water as HOH. And then when you kind of think about hydrogen leaving or being accepted, it makes it a little bit easier to visualize that way. So this NH3 is reacting with water. And notice that NH3 is now going to be NH4. So that hydrogen, okay, it's a weak base. Some bases accept that proton. So it accepted the proton from water here. So now NH3 becomes NH4, okay, which now with a positive charge because now you accepted an extra proton. And then that leaves, if you take this away, okay, now you're just left with a hydroxide ion over here. So it produces hydroxide in this reaction. So even though looking at NH3, you don't necessarily know if it's an acid or base just on how it looks, because it produces hydroxide in the actual equation, it is a weak base. So that is something that you should note. You will see ammonia quite a bit. Okay, so we're going to talk a little bit about conjugates. So the word conjugate just means partner. Okay, and this goes along with the Bronsted-Lowry definition. So the base, so let's stick with ammonia because we've been talking about ammonia, becomes what's called a conjugate acid. So every base has a conjugate acid. Every acid has a conjugate base. It's got a conjugate buddy. So if our base is NH3, okay, again, bases accept their proton acceptors. So it's going to accept that proton there, that hydrogen, and it's going to become NH4. So NH3 would be my base. So NH4 would be my conjugate acid. Okay, so again, conjugate just means it's partner. So think about Bronsted and Lowry and what that actually means as far as whether it's donating a proton or whether it's accepting a proton. Okay, so another example would be if I had HCO3. Okay, that's the conjugate base of H2CO3. So if this is a conjugate base, that means that this is an acid. And again, that acid's got that hydrogen out front. So this, as an acid, donates one of those hydrogen ions, one of those protons. So you have H2CO3 giving up a hydrogen. Okay, and now you'll notice that that is now H2, just goes down to HCO3. So there's that hydrogen there, HCO3 there. So every acid has a conjugate base, every base has a conjugate acid, and you can tell what those are if you understand what an acid does and what a base does. So acids donate a hydrogen and bases accept that hydrogen. So for example, let's look at this. What is the conjugate base of H2SO4? Okay, so if I'm asking about a conjugate base, I know that this is an acid, okay, because an acid has a conjugate buddy. So H2SO4. So acids donate hydrogen. They donate that proton. So if I take away one of those hydrogen, then I get HSO4. Okay, so essentially I'm losing a hydrogen. So H2SO4 donates one of those H's and it becomes HSO4. So this is the conjugate base. Here's my acid. After it donates it, now these have a kind of a relationship and it's a conjugate acid-base pair. Here's my acid, here's my conjugate base. So this is losing a hydrogen in order to become its conjugate base. Also notice that in H2SO4, there was no charge. But here, if it loses one of those hydrogen ions there, you know that you have one less hydrogen. So no longer is this neutral, but now you're going to have, because you lost that proton, now you have a negative charge involved with that. Okay, so the charges will change too once it starts moving around those hydrogens. Okay, so let's look at this one. What is the conjugate acid of SO4 2-? Okay, so again, I'm looking at a base because it's asking me about the conjugate acid. So bases, again, they are proton acceptors. So my base was HSO4. It gained that HSO4 in order, and there's my conjugate acid. So that's how I know this is a base, because this is gaining that hydrogen, which is what bases do. They gain hydrogens, and now this becomes HSO4. And again, notice the charge here. This was a 2- charge, but if I gain that proton, now I gain one of those positive charges. So now it's just HSO4 with a 1- charge. Okay, so again, just paying attention to whether you have proton donors or proton acceptors. So the conjugate just means partner. Bases will pick up a hydrogen to make its conjugate acid. Okay, and then acids will donate that hydrogen to become a conjugate base. And again, those are their pairs. Conjugate just means partner, and they have a buddy. Okay. Okay, so I just want to show you an example of what this looks like in an actual equation. So here, HCl plus H2O. Now, H2O is one interesting molecule for lots of reasons, but H2O can actually act as an acid or it can act as a base. So it's actually something called amphoteric, which can act either way. So you have to look at what it's reacting to. But either way, I just wanted to show you, in order to determine which one's the acid and which one's the base, you have to look at that product side. You have to try and figure out, well, what's happening on the other side. So you'll notice HCl on the other side became just Cl. So it donated that hydrogen. So that's how I knew that's my acid, because it donated. H2O became H3O on the other side. It accepted that hydrogen. So this one donated it. This one accepted it. So because this one accepted it, this is my base. So acid and base. So you have to look at the products to try and determine what your acids and your bases are, and then you can look at your conjugate acid and your conjugate base. Okay. And this is acidic because it's got that hydronium content in there. Okay, I'll show you another example. Now, if I said which one's the acid and which one's the base, again, you have to look at what's going on the product side. So NH3 on the other side became NH4. So it gained that hydrogen. So because it gained that hydrogen, I know that that's my base. It's an acceptor. H2O, again, think of it as HOH. It just became OH on this side. So that hydrogen HOH, that H jumped over here, okay, and to just leave OH. And again, this is basic because of that hydroxide. So pay attention to your product side. And again, notice you have double arrows now. Double arrows just means the reaction is reversible. It can go either direction, okay? But just for our intents and purposes, keep the reactants as always the left side and keep the products as always the right side. And that'll kind of help too, because even though these are reversible, that means they can go either direction, okay? Okay, so let's look at a couple examples of how this looks. So again, I've already talked about every acid and every base has a conjugate buddy. So again, now I'm going to give you an equation and ask you to determine, well, which one's the acid and which one's the base? And then you can also determine which one's the conjugate pair. So let's look at this here. So HF plus H2O. So again, look at this side over here. You'll notice that HF became just F. So it donated that hydrogen, right? It lost that hydrogen there. So because it gave that up, again, according to Bronsted Lowry, that is an acid. So HF became H. It donated that. That's an acid, which then makes this its buddy. Okay, that makes that its conjugate base. It's just the opposite. Okay, so again, if you have an acid, it's got a conjugate base pair. H2O on the other side became H3O. It gained that hydrogen. So because a base is a proton acceptor, that's my base. So if that's my base, that means that this has to be my conjugate acid. Okay, so notice you have an acid base and a conjugate acid and a conjugate base. So every acid has a conjugate base. Every base has a conjugate acid. So you have to look at that side. And notice if you went the other direction. So look, this is a reversible equation. It's got the double arrows there. So let's just look at this for a second. This is my base, right? So if this is my base, if I look at it on the other side, it gains that hydrogen. So that's how I would know, hey, here's my base. H3O lost. If I go this direction, it went from H3O to H2O, it lost. So there's my acid. So this works both directions. Okay, so when you label acid and base and their conjugate base pairs, you can still go the other direction and it'll all still work. Okay, so let's do another one here. So identify. So this is an example of something that you'd be given, and I would ask you to identify the acid and the base on the reactant side. And again, keep the acid base on the reactant, the left side. Okay, so reactants on left, products on right. So identify the acid and base first, and then you can identify what the conjugate acid and the conjugate base are. So pay attention to what happens on this side. So H2CO3, what does it do on the other side? Okay, we will notice it actually donates. So H2 just became H. It lost that proton. So if it loses that proton, that is an acid, okay, because it lost that hydrogen there. So if H2CO3 is my acid, H2O is then my base. And if we look at H2O, H2O gained that hydrogen. Okay, this one donated it, this one accepted it. So now H2O becomes H3O. So there's my acid and there's my base. Okay, and on this side, we can do the conjugate pairs. So H2CO3 is connected to this one. So if this is my acid, then this becomes my conjugate base. Okay, it's the opposite. And then H2O gained. So this is my base, which makes this my conjugate what? Acid. Okay, so again, you can identify these based on what's going on the product side. So if I were just to look at these on the reactant side, you can't tell. You don't know. You have to look at that product side. You have to see what's happening on this side to figure out, well, where did that hydrogen go? Which one donated it? Which one accepted it? What does that look like? Okay, let's do one last practice one. So again, same thing, label the acid, base, conjugate acid, and conjugate base. So here's my two reactants. I have Cn negative and HCO3 negative. I have to look at this side here. So notice Cn negative is on this side. It becomes HCN. So what did it do? Did it lose or did it gain? Well, it gained. So Cn becomes HCN. So if it gains, that is my, shout it out, base. Good. Okay, which makes then HCO3 my acid, because if you'll notice, HCO3 just becomes CO3. It lost that H, so now it's just CO3. So this is my base, this is my acid. Okay, so once you determine your acid and your base, now you can go to the product side. So if this is your base, then that makes this your conjugate acid. Okay, and if this is your acid, that makes this your conjugate base. Okay, and again, I'm going to show you again, just because this is reversible. So if I go this way, HCN, this is my acid, right? If I go this way, it loses. Okay, so this would be my acid, this would be my conjugate base. And over here, this went from CO3 to HCO3. So it gained, so there's my base, and that would be my conjugate acid. So again, it works, it's reversible, it works both ways. So just keep in mind when you're doing this and you're trying to determine acids and bases and their conjugate pairs, determine which one donated, there's your acid, which one accepted, there's your base, and then every acid has a conjugate base pair, and every base has a conjugate acid pair. Okay, good. So from this, know the difference between Arrhenius and Bronsted Lowry. So again, remember Arrhenius just said, hey, acids give that hydrogen and bases give that hydroxide. So you can easily tell if there's an H or an OH, what an acid and what a base is. And then Bronsted and Lowry later on added to that and said, hey, acids are proton or those hydrogen donors, and then bases are those proton acceptors. So know the difference between what those two definitions are. Neither one is completely wrong or right, but they together make the most sense as far as acids and bases go. And then know your 6 strong acids, write those down, commit those to memory, know what those are, be able to recognize those along with your strong bases, and then know that NH3 is a very common weak base. So NH3 is ammonia, so it's a very common weak base. Okay, and then on my next lesson, we'll do calculations of pH, values and things like that. So this was just over the intro to what an acid and a base and what those look like. So nice job. Thanks for hanging with me.